Hello, this is the Universal Gravitation according or written by Sir Isaac Newton. Isaac Newton first published this idea on gravity in a famous book called Principia Naturalis, which was published in 1687. Now in this book, Newton states that every mass attracts every other mass with a force called gravity that varies directly with the masses involved and inversely with the distance between them squared. It was in this book that Newton tried to account for the forces that acted between an apple and the earth, between you and the earth, and even things in space like between the moon and the earth, and even the sun and the moon. He was quite successful in doing so. So this little video is the first of two. The first one will explain universal gravitation to you, and the equation goes along with that. The second one will show you how to use the formula to do some calculations with that. So moving along, let's take a look at what this particular law says. So if you imagine this circle to be the Earth, and a person standing on the Earth, then he's at the radius of the Earth away from the center of this particular Earth in here. This person will experience a force of gravity between him and the Earth equal to F sub g. Now, if we were able to take the same person, hopefully in a spacesuit, and move him to a distance that is equivalent to 2 times the radius of the Earth away from the center of the Earth, then he will experience a force that is only 1/4 the strength of that force as experienced on the Earth's surface. Now, I can't show you in this particular one, but you can imagine that if we could take the same thing and put them way out here at a distance equal to, say, 10 times the radius of the Earth, and put the little man sitting out there, then the force that this person will experience will be equal to 1/100th of the force gravity that he would experience on the Earth. That's what I mean by the inverse squared of the distance and the force relationship. Okay, so that idea then, as presented by Newton up here, can be rewritten in a more typical physics way into a formula. And the formula looks something like this. The force of gravity, or the force of attraction between two masses, is directly proportional to the masses multiplied by each other, and is inversely proportional to the distance between them squared. Something like that. Okay? This little symbol that looks kind of like a fish in there means proportional to. That's what that one means in there. Okay? Now, to change any proportional expression or proportionality into equation, we need to put in a constant and to replace the proportional into an equal sign. And we can do that if we do this. And let me put it back a little higher. Okay. The force of gravity between two objects is now equal to the mass of one object times the mass of a second object divided by the radius squared, and we put into here the proportionality constant called g. We now change it into an equation which states basically called the universal gravitational law into here. Okay? Now, Newton never stated this law. Newton stated the proportionality when there. In order to change it from the proportionality into this equation, you need to find the value of g. And that was done by somebody called Henry Cavendish kind of a strange little person, but he did the work. He came up with G, and you can read about it and look him up if you want to into here. Anyways, he came up with a value for G. The value for G, capital G, which is called the universal gravitational constant, and that is equal to the following number: 6.67 times 10 to the minus 11 newtons per meter squared per kilogram squared in modern terms. Of course, cabinet did it different, but that's in there. That's what G stands for. M, 1 is 1 mass. It could be the Earth, it could be something else measured in kilograms. M2 is the second mass. You need 2 masses to generate a force. And of course, it would be measured in kilograms as well. And R is the distance between 2 objects, center to center. The 2 objects. And it will be measured in meters. It's in there like that. Okay. Now, is there any proof for this equation, or we just assume that it's correct? Yes. I give you a couple of proofs quite easy along the way into here. Okay? I'll give you 2. First one I'm going to give you is to use 2 equations, one being this one that I have here, and one being the other one, to show this equation is right. For example, let's suppose I ask you to calculate the weight. Now the weight is equal to the force of gravity, and that's to be calculated by taking the mass that an object has and multiplying by the acceleration of gravity near the Earth's surface. Now remember we did this. This would be 65 kilograms. And multiply that by 9.81. Put my number in here. And if we work that out, we will get 640 newtons, which is the weight of a person on the Earth. I want to do the same calculation using the universal gravitational law here. Okay, to do that, you need to pull out the equation. The equation is force of gravity equals Gmm all over r squared. So what we need to do is to take a look at 2 masses. Well, what's holding it down? And that is the mass of the Earth. The other mass would be your mass, and the distance will be the radius of the Earth into here. So let me show you how we work this. Put in the constant, 6.67 times 10 to the minus 11. Take the mass of the Earth, which I can look up in a book. It's 5.98 times 10 to the 24th kilograms. Take the mass of the person, which is 65 kilograms, and then we divide that by the radius of the Earth, because that's where the person is standing, which just happened to be 6.38 times 10 to the 6 meters, and then that has to be squared. So if I pull out my calculator, there's my calculator there. Okay, I'll move it over there, and then we will put all these numbers into the calculator and see how this works. Okay, so 6 point, oops, won't work, let me try again, 6.67 exponent negative 11. Well, it looks like my calculator is going a little haywire, and I'm not quite sure why it works. Probably the program I'm using for this, but that's not a big deal. It's not want to work. Let's, anyways, yeah, word for it. If we work this out on your calculator, the force of gravity will come out to be 640 newtons. In other words, the answer that we got by the old equation And the answer we have by the same equation, are exactly the same. That tells you that this equation seems to work. That's one proof. Okay, so let me give you a second proof in here that this equation does work. And we already have an equation that says that force of gravity equals m times g. But we also know that this equals another force of gravity, gmm, all over r squared. In other words, these two equations, if they both tell us about the force of gravity right in there, then it should be equal to each other. Since this mass represents the mass of the mat, and so does that one, it's the same mass on both sides, which means that the acceleration of gravity can be calculated from a version of the universal gravitational law, which looks like that. So if we put into here the constant 6.67 times 10 to the minus 11, and we multiply it by the mass of the Earth, because that's what's left there, and we divide that by the radius of the Earth, 6.38 times 10 to the 6 squared, we do that into here, then you will find out that the acceleration of gravity is equal to 9.8 meters per second squared, which is in fact the same value that we get if we calculate the acceleration of gravity by other means. All right, now that you've seen it works, let me make some examples, and I'll do that in the next video.